This is Lab 5, Faraday's Law. In this lab, we are to observe and record data while dropping a magnet through a tube of tinfoil, as represented by the image to the right. Then create a computational model from this and analyze these results with our expectations. Some assumptions made in this lab is that the tube is held exactly vertically during the experiment and the magnet does not hit the sides of the tube while falling through the aluminum foil tube. Some major concepts used in this experiment. Faraday's law, a changing magnetic field and changing magnetic flux, can induce a current which can be found for a ring within the tube as the magnet falls. Biot-Savart's law, this describes a magnetic field created by a current-carrying object and can help define the amount of force the magnet exerts on each ring. Newton's second law, which helps describe how the forces on the magnet cause it to fall with a certain velocity, and Newton's third law, which allows us to apply Lenz's law to find out how much force is exerted on the magnet as it falls. Dropping the magnet. All the way to the right is an image before I drop the magnet through the aluminum foil tube. All the way to the left are the dimensions of my tube, 30.1 centimeters in length, 1.3 centimeters in thickness, and 2 centimeters for an inner radius. In the center is a table with each of my trials and elapsed times, with an average time of 0.99 seconds within the tube. I noticed that the magnet fell slower than it would in actual free fall, with no tube present. If a ferrous tube were used instead of the aluminum foil, the magnet would not fall through the tube since it's magnetic. Aluminum foil is conductive, but not magnetic, which is why this is not the case in this experiment. This computational model represents the magnet falling through the aluminum foil tube. The total time in the model is 0.921 seconds. The real-world time was more than the computational model. This could be due to the experimental value of μmag from Lab 3. However, I found that higher values of the moment for the magnet caused the time of the computational model to be closer to the real-world average found in this experiment. A way to make this a more accurate model would be to increase the amount of rings used. In terms of the velocity versus time plot, within the first 0.1 seconds, the velocity is the greatest because the induced current is being created by the falling magnet. After that, the velocity plateaus as the induced current causes a force on the magnet upward, and finally increases negatively during the last 0.1 seconds at the end of the tube. These are some major code changes in my GlowScript code. Starting in the top left-hand corner, initializing the tube and the magnet, calculating the magnetic field and the magnetic flux, moving to the right-hand column at the top, calculating current, then the magnetic field for a ring in the tube, and finally calculating force, velocities, and positions for the magnet. Some computational model questions. The intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in the opposite directions. Which color corresponds to clockwise current and which counterclockwise? Blue is counterclockwise current and red is clockwise. The change in flux points downwards. Because of this, the counterclockwise induced current is opposite of the right-hand rule that would otherwise indicate a clockwise downward change in flux. What happens to the dynamics of the system when you flip the magnet? If the magnet's flipped, the magnet falls faster. Since the poles of the magnet are reversed and the magnetic field of the bar magnet is reversed, the magnet helps itself fall faster since the forces exerted by the induced current on the magnet are all reversed. Some remaining questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The current would increase and it would fall slower, which increases the fall time of the magnet. Using Ohm's law, if the resistivity decreases, the current will increase. If the current is increased, the upward force will resultingly increase as well on the magnet. What if the holes or slots were cut into the tube? How would this affect the ring currents in your model? With holes, there would be less magnetic fields induced and less magnetic fields present since there is less rings in the tube to have an induced current. The magnetic force is then less and causes the magnet to fall faster through the tube.